Have you ever wondered how machines can recognize your face in photos, translate languages instantly, or even beat world champions at chess? The answer lies in one of the most fundamental building blocks of artificial intelligence, the feed-forward neural network. Today, we're going to decode the mystery behind these powerful algorithms that are literally reshaping our world. By the end of this video, you'll understand exactly how these networks think, learn, and make decisions. So buckle up, because we're about to dive deep into the fascinating world of neural networks. Let's start with the basics. A feed-forward neural network, or FNN, is inspired by how our brain processes information. Just like your brain has billions of neurons connected together, an FNN has artificial neurons arranged in layers. The term feed-forward means information flows in only one direction, from input to output, like water flowing downstream. No bloops, no going backward, just straightforward processing. Think of it like an assembly line in a factory. Raw materials, that's your input data, enter at one end. Each station, that's our layers, processes the materials and passes them to the next station. Finally, we get our finished product at the end. That's our output. Unlike other neural networks that might have feedback loops, feed-forward networks are beautifully simple in their one-way flow of information. Now, let's break down the anatomy of a feed-forward neural network. Every FNN has three essential components. First, we have the input layer. This is where our data enters the network. Each circle you see here is called a node, or neuron. If we're recognizing handwritten digits, each input node might represent one pixel of the image. Hidden layers and layers. Next, we have hidden layers, this secret sauce of neural networks. These layers do the heavy lifting, extracting patterns and features from our data. You can have one hidden layer or hundreds. It depends on your problem's complexity. In image recognition, the first hidden layer might detect edges, the second might recognize shapes, and the third might identify objects. It's like building understanding layer by layer. Output layer. Finally, the output layer gives us our answer. For a digit recognition task, we'd have 10 output nodes, one for each digit from 0 to 9. The node with the highest value is our network's best guess. But here's where the magic happens: weights and biases. Weights are the strength of connections between neurons, like the volume knob on a radio. Biases help neurons make decisions even when inputs are 0. These are what the network learns during training. Let's see this network in action with a simple example. Imagine we're trying to predict house prices based on size and location. Step 1. Our inputs enter. Let's say house size is 1,500 square feet and location score is 0.8. Step 2. Each connection has a weight. We multiply each input by its weight and add them up. So if our weights are 0.5 and 0.3, we get 1,500 times 0.5 plus 0.8 times 0.3 equals 750.24. Step 3, we add the bias. Let's say it's 100. Now we have 850.24. Step 4, this sum goes through an activation function. Think of it as a filter that decides how strongly this neuron should fire. Popular choices include ReLU, which simply outputs the input if it's positive, or 0 otherwise. This process repeats for every neuron in every layer until we reach our final prediction. Remember, information only flows forward, never backward. That's why it's called a feed-forward network. But how does the network learn to make better predictions? Meet backpropagation, the learning algorithm that makes it all possible. Step 1. The network makes a prediction. Let's say it predicts a house price of $300,000, but the actual price was $250,000. That's an error of $50,000. Step 2. This error travels backward through the network, hence backpropagation. Each neuron asks, how much did I contribute to this mistake? Step 3. Based on each neuron's contribution to the error, we adjust the weights and biases. If a weight caused too high a prediction, we reduce it. If it caused too low a prediction, we increase it. This process uses something called gradient descent. Imagine you're trying to find the bottom of a valley while blindfolded. You feel the slope and take steps downhill. That's how the network finds the best weights. We repeat this process thousands or millions of times with different examples, and gradually, the network gets better and better at making predictions. Let's talk about activation functions, the decision makers of neural networks. Without them, our network would just be a fancy linear calculator. RLU, or rectified linear unit, is the most popular activation function. It's simple. If the input is positive, output it as is. If it's negative, output 0. It's like having a one-way valve for information. Sigmoid squashes any input into a range between 0 and 1. It's great for binary classification, like determining if an email is spam or not spam. Tan is similar to sigmoid, but outputs values between -1 and 1. It's often used in the middle layers of networks. Each activation function has its strengths. RLU is fast and works well in most cases. Sigmoid is perfect for probabilities. Tan provides stronger gradients for learning. Choosing the right activation function can make or break your neural network's performance. Feedforward neural networks are everywhere. Let me show you some amazing applications. Image classification, from medical diagnosis using X-rays to sorting your photos automatically. The network learns to recognize patterns in pixels and classify what it sees. Natural language processing, sentiment analysis in social media, email spam detection, and language translation. These networks can understand the sentiment behind your tweets or determine if that suspicious email is actually spam. Financial predictions. Stock market predictions, fraud detection, and credit scoring. Banks use these networks to detect unusual spending patterns that might indicate fraud. Game playing, even game AI, from chess to Go to video games, feed-forward networks help create intelligent opponents that adapt to your playing style. And we're just getting started. Autonomous vehicles, drug discovery, climate modeling, the possibilities are endless. Feed-forward neural networks have some incredible advantages. First, they're universal approximators. Given enough neurons, they can learn almost any pattern in your data. They're also highly parallelizable, meaning they can process multiple inputs simultaneously, making them perfect for modern GPU computing. Plus, they're incredibly versatile. The same basic architecture works for images, text, numbers, you name it. Limitations. But they're not perfect. They struggle with sequential data. Imagine trying to understand a sentence by looking at all words simultaneously rather than in order. They can also overfit, memorizing training data instead of learning general patterns. It's like a student who memorizes answers instead of understanding concepts. And they're data hungry. You need lots of examples for them to learn effectively. Ready to build your own? Here are some pro tips for implementing feed-forward neural networks. Start simple. Begin with 1 or 2 hidden layers. You can always add complexity later. More layers aren't always better. Pre-processing is crucial. Normalize your input data, handle missing values, and consider feature scaling. Garbage in, garbage out. Experiment with hyperparameters. Learning rate, batch size, number of epochs. Think of it as tuning a musical instrument for the best performance. Always use validation data to check if your network is actually learning or just memorizing data. Split your data into training, validation, and test sets. Watch out for vanishing gradients in deep networks, and don't forget regularization techniques like dropout to prevent overfitting. And that's feed-forward neural networks in a nutshell. We've covered how they work, how they learn, their applications, and how to use them effectively. Remember the key points. Information flows forward only. Learning happens through backpropagation, and activation functions provide the nonlinearity that makes it all work. What applications of neural networks excite you the most? Drop a comment below and let me know. If this video helped you understand feed-forward neural networks, smash that like button and subscribe for more AI content. Next week, we'll dive into convolutional neural networks, the powerhouse behind modern computer vision. You won't want to miss it. Thanks for watching, and I'll see you in the next video.